this session. Actually, red are almost at the edge of the universe, but most importantly, are actually at the edge of all the classification algorithms, the reliability of photometric redshift, and all the cross-matching. It's all, we are trying to scratch the end of all these methods. So what I'm going to present, I will do a brief introduction on high redshift AGN, and I will focus mainly on the selection of high redshift sample and the photometric redshift estimation. And at the end, I will show some properties of this high redshift AGN using X-ray spectral analysis and some shading fitting with SIGAL. But this last part is actually, the results are preliminary. So I will start with that all galaxies, most massive galaxies, host a supermassive black hole in their center, at least in the local universe. And the X-rays is the most efficient way to find this AGN for the obvious reasons. But my point here is that sometimes we forget about the numbers. So here is the Chandra DB field south, 7 megasecond exposure time. So we have around 1,000 sources in the good catalog. And this actually corresponds to more than 25,000 AGN per square degree. So if we compare this with the optical images, we see here a part of this of the Chandra field of view that is actually one of the deepest HST image. And here we have billions of sources, galaxies. However, if we check the AGN, it's only 200 AGN per square degree. So this is important why we use X-rays for AGN. Okay, all this, what I said before, doesn't apply a lot in the high redshift universe, because here the space density of high redshift AGN is very low. It's one per gigaparsec. So we are limited our sample because of the limited sky area. So we need a large sky X-ray observation to reach all these rare, actually, objects. On the other hand, we have the optical surveys that they are actually with a wide field surveys, or the deep, for example, from Subaru surveys, we can have a large number of AGN at high redshift. So what we want to do is to increase the X-ray sample in this redshift in order to correctly study the growth and the evolution of the AGN population. So till now, some tools to study the evolution of the AGN is the X-ray luminosity function, and this is very well constrained up to redshift 3. However, even though at higher redshift, there are many works finding and studying AGN above redshift 3. We have some many discrepancies in the XLF, for example, even within the X-ray samples and surveys. And also we have large discrepancies with the simulations. And also when we consider the black hole accretion density, we have differences that is maybe even 5 times higher than the X-ray black hole accretion density. So for all of this, we need a large sample of high redshift X-ray AGN. So this is a work that was published this year in January. So this was the first attempt to increase the area of our sample. So in this work, we actually used the XMM XXL northern field, and we have accompanied this sample with the deepest field of the Chandra DB fields, and also data from the cosmos, and we selected more than 600 sources at a redshift greater than 3, and we were able to constrain the XLF. And also we used for all the sources simultaneously the same spectral analysis fitting. We included all the photometric redshift information. So we're having a very good XLF. However, at the bright luminosities, we are lacking sources, so we need actually even larger areas to trace these sources there. And here is some the other results on this paper with the black hole accretion density. The point is that we increase the black hole accretion density compared to the previous work. And on the right, you can see it as versus redshift. And with this purple shaded region is the X-ray black hole accretion density. And we found that if we put some cuts in the stellar masses, we actually agree very well with the simulations. And the new part here, these data points, they are coming from the James Webb Space Telescope, the infrared selected AGN. So we can see that we have discrepancies there now. And we try to show that we have some hints actually that this population trace different AGN population with different properties. And this is basically the stellar mass of the host galaxy and the black hole accretion rate. So in order to find exactly what's going on there, we need even larger sample of high redshift X-ray AGN. So the opportunity came with a 4XMM catalog, the full sky. We have 1,200 square degrees. But in order to select high redshift AGN, we need the deep optical data and to have near infrared coverage. So in this work, we actually selected the DES field that covers almost 5,000 square degrees. You can see it here with the blue color. And this field actually includes all the three big homogeneous X-ray fields, the XMM, XXL, both fields, plus the stripe 82. And if we do all the maths with the more catalogs and all of this, we end up with almost 200 square degrees with deep DES optical photometry and VHS data. So in this region, we have from the 4XMM catalog, we have almost 72,000 X-ray sources that have DES or VISTA counterpart, and we have a completeness that reaches 92%. And just here, I'm comparing with the result of the XMM XXL North that we had even deeper HSE from the Subaru optical photometry. That out of the high redshift sources selected there, we were able to find that 86% have counterpart in the DES catalog. So we are good at this as well. And here we use the classification from the XMM to Athena product from Hugo. And we actually, out of these sources, we have 68,000 sources that are classified as QSO or AGN. So out of this sample, we tried, as I will show later, to estimate the photometric redshift, and after to do the SCD fitting with the available photometry we have. So this is the starting point of this work. And in order to do this, as Angel Ruiz explained earlier in the morning, in the high redshift, actually, we cannot go with machine learning because there we don't have the training sample to go above 3 or 3.5. It's impossible to train and to have good results with a machine learning algorithm. So the only way there is to go through SCD fitting. To use templates for the SCD fitting and to find the photometric redshift. So here I'm showing you saw this plot again today. It's the photometric redshift versus spectroscopic. On the left is for point-like sources, and on the right is for the extended sources. Okay, we care a lot about the point-like sources that we expect to have the high redshift sources. We have a fraction of outlier is 22.7%. That compared to the previous work with Alfaro, we are more or less there. With some work, we are lower. And so here the point, you are seeing this blob. And as Angel said earlier, these actually are coming from the degeneracies in the templates we are using. And in order to in order to understand better where this problem is, I just here I plotted the fraction of outliers versus redshift. So at each point, it's a fraction of outliers for all sources above this redshift. So actually, this blob here, it's actually this peak that it's around 3, redshift 3, and here reaches around 40% of outliers. So, but you can see, okay, it's gray, very faint, but here at 3.5 redshift, we are falling up to 10% of the fraction of outliers. So this is the reason in this work we selected sources above 3.5 to avoid actually this part here. So the blue line here is actually, we use a training sample with a spectroscopic redshift. And actually here, the blue sample is containing sources with different coverage in photometry. So it might have DES, infrared, DES WISE, or it's a mixture. But here, if we see the red line, the bottom one, actually, that it will have the full, all the bands available, 10 bands from near optical to mid-infrared, we can see that we have a lower fraction of outliers as expected. And we reach again above 3.5 is the percentage of outlier is again 4. And it's actually above redshift 4, we go to 5%, and it's actually diminishes at the end, as you can see here. But this is for the training sample. So here is the same plot as before. So you have this line, the red line here. It's actually the results from this. And here I wanted to show this plot. These dashed lines here that is going up, it's actually the results from HDSS and pan-stars. And even though up to redshift 3, we have the same trend with DES, here these surveys make the fraction of outliers pops. And this actually, because these surveys are not deep enough, so to constrain at this high redshift. And on the other hand, we have this flat line here that is coming from SDSS. Sorry, the other is pan-stars and sky mappers. Sorry. So this black line is SDSS that we see that compared to DES at high redshift is higher. This is because it's not deep enough. But here, the interesting part is that we don't have this bump at redshift 3. And this is because SDSS have the U band available. With DES, we don't have this band. So it's important to have and the U band actually and deep photometry to go on with this. And here I overplot as well with the blue dashed line. It's actually from a sample of optically selected QSOs that I will show later on in the presentation. It's not X-ray AGN, but we see the following trend. But we have here a larger number of sources, and we have again 10% fraction of outliers above 3.5. So here is the distribution of the redshift. On the left, the red and blue is the spec Z and photo Z distribution. On the right, it's just the point light and extended sources. And the first thing we notice is this actually here at redshift 5, it's we checked a lot. And at the end, we realized that these are actually stars. So here I plotted all the Gaia cross match of the whole sample, and you can see that it's actually two regions here. Here is actually the AGN, and here down is the stars. And I have color coded with a different AGN probability. But even here we have some with probability of 0.9, but they are actually stars. So we had to exclude it by hand, and the point here is that even though the classification, the ML classification for AGN class is 5%, that corresponds to the full population. When we go at high redshift, this percent is going to 12, 13%. So when we're going to high redshift, all these reliabilities of everything, cross-matching, classification, tend to be totally different. And here it's actually the final numbers after we exclude these stars. And though from the training sample I showed earlier, we expect to have 10 to 15% of outliers. And these sources actually are low redshift that contaminating the high redshift sample. In order to do this, we went to TPZ that we selected the sources that up to 3 where they have a very high reliability and accuracy, and we selected the very good sample that the PS is more than 0.9. And actually, we were able to cross-match, okay, the two methods and to exclude sources that they are actually contaminating our high redshift sample. And actually, the percentage is 18%. That is very close to what we were expecting to be the false positive high redshift sources. So actually, this is the high redshift sample. Okay, we need to do more work on all of this. And I will pass a little bit fast to the properties of these high redshift sources. So here I use the Seagal algorithm, and for the X-ray high redshift sample, on the left you can see some examples of ACD that are classified as type 1 through the ACD fitting, and on the right the type 2 AGN. And you can see the different components, the stellar, and here, for example, on the left, the AGN component dominates the ACD, the total emission. And we found out if we put some reliability criteria on the ACD fitting, we have around 500 sources with good ACDs, and actually half of the sources are type 1, and the other half is type 2, according to the ACD fitting method. So here is just just the averaging is the median ACDs for type 1 and type 2, and you can see that for type 2 AGN, okay, the host galaxy dominates the emission, while here on the type 1 we see the opposite trend. It's okay, what I expected. And here is some X-ray properties. Here we want to do more, but okay, here just the distribution of the high redshift sources in the flux and redshift plane. We use actually the XMM to Athena catalog with spectral fit, but these sources did not include any redshift information inside, but at least it gives us a hint of the X-ray properties, the obscuration in X-rays. And here is the distribution of log NH for the two ACD type 1 and type 2 of the Seagal. So we can see that in general, the type 1 ACDs tend to have lower log NH, and type 2 higher log NH. But this is actually the spectral properties are coming without redshift information. So what we expect is actually to move all this distribution, to move the log NH to higher NH. And actually in the paper that we were published from XMM XXL, it's actually we found that the more than 60% of the sources in X-rays is highly obscured. And this is because of the ISM and plus the obscuration of the torus. And the final part, it's actually we wanted to compare this high redshift X-ray sample with the optically selected QSOs. So there was a paper 2023 from Yang and Sen that they selected in the same area, in the DES area, they selected almost 1.4 million QSO candidates. The reliability of this selection is they're supposed to be broad line, and the reliability is very high, it's 95%. So inside the XMM desk, the 200 square degrees that we are using in the same area, we have 50,000 optically selected QSOs, and out of those, we have 800 high redshift AGN with rates above 3.5. So on the right, you can see on top, it's actually in this region is the overlapping, the X-ray sample, the full sample at all redshift, and the QSO sample. So you can see that even in the full sample, we have the overlapping is very small. Okay, this is going even greater when we go to high redshift, where we have almost 10% in both sides. 10% of QSO are X-ray detected, and 10% X-ray detected are selected as optically selected QSO. So the idea was to compare these three samples, actually, the common, the X-ray only selected, and the QSO optically QSO only selected samples. And here is just the, with SCD fitting, is the median SCD for okay, not for all X-ray sources, for the QSO sample, that you can see that in the optical UV part, we have this trend. Okay, and we will apply the criteria, the quality criteria. We have 600 good SCDs. And actually, we were able to verify the reliability of their method. Actually, we find that 90% through SCD fitting, we have 90% type 1 AGN. And this is the solid lines is again the median SCDs. For the QSO only sample is the blue here. The common sources that's actually very similar to the QSO sample. And as well, we have the X-ray sample that is falling here. And on with the dashed lines, I saw the median host galaxy contribution to the total emission of these sources. And we can see that the optically selected QSOs have lower masses compared to the X-ray sample. However, with this, okay, because the AGN is totally dominating, we are not quite secure about this result. And this is something we want to work more to try to figure out how we can do better in the QSO SCD fitting to find actually the properties of the host galaxy, because the uncertainties there are huge. And here on the left plot, we can see the magnitude distribution, the I band for the QSO sample in blue. And we can see the common sources are these shaded gray sources here in the very bright end. And we have the red distribution that's actually the X-ray sources. So from this plot, we can see, it can tell us a lot about why we have this small fraction of overlapping between the two samples. The first thing is that in the X-ray sample, we have the half of the sample is very fainter than the optically selected QSOs. And if we look in the top right plot, it's actually the same distribution, but I have split it, the X-ray sample with SCD type 1 and type 2. So actually this population here, it's all the type 2 AGN. That's why this is the reason why they are not in the QSO broadline sample. Now the problem, the other one is, okay, we have some from type 1 sources that they are mapping the same optical distribution. So we have part of the sources are in common. However, we have a large portion of type 1 X-ray sources that are not selected in the optically selected sample. And this, if we trust the SCD fitting results, we find that this X-ray type 1 non-optically selected AGN, they have actually higher polar dust in their system. So this means that they might be red QSOs. So this is something that we discovered lately, so I didn't have time enough to do some more things. But these two plots explain why it explains actually that we have two different populations. And okay, here is the summary. The point is that we need a lot of more work to select high redshift sources. And even in this, we need to do some more refining in everything. And I didn't speak a lot about the cross-matching, and we need some more work there. And we need to find out, actually, we need to use both ML algorithms and ACD template fitting algorithms for the photometric redshift estimation, because one is working well in a redshift regime and the other. And this was a nice point that probably we will discuss later on. It's actually about all the classification methods that we said earlier. It was mentioned earlier that all the classification algorithms are working for the bulk of the population, but how we can do it to work in the corners of these populations, in the rare objects. And okay, to summarizing, yes, we derived some properties of the high redshift sources. We found that half of the population are type 1 and the other one is type 2. That agrees with the X-ray classification, but here is something we would like to do to rerun the spectral analysis using the photometric redshift distribution we have. And comparing with the optically selected sample, we find that these two samples are totally different. And here, actually, we need to do some more work to apply the same criteria of the optically selected sample to the X-ray sample. And I think that's all. So thank you very much.
Nice presentation. First, if there's any question on Zoom, please either raise your hand or send a message in the chat. And in the meantime, if there's any question in the room. And don't forget to introduce yourselves for the people on Zoom, please. Thanks.
Mara Salvato here. When you were showing the comparison between the PhotoZ and the SpecZ for the point-like sources and the extended, here you have a lot of sources that are classified as extended in optical, but they have a redshift that is higher than 1.
Okay, this was a thing we are still working on it, because we have this morphological classification that there are 4 classes. Most probable, likely, point-like, and there's same 2 classes for the extended sources. So this classification is divided into most likely and probable point-like and extended. But we run this when we use for extended sources only the secure extended sources. So the results were this 15% went down to 10%. But after it was again...
I'm not criticizing your PhotoZs. I am just saying that it is very difficult to explain in nature objects that are classified as extended in optical, a redshift higher than 1, if the classification is done with ground-based telescope with CCDs and pixels of this size. If you put a galaxy of typical size at redshift 1.5 and be still extended, if you bring it back here, it
Will
is
be-
something that doesn't make physical sense. At least it is not an object that we know. So what I'm saying is that the objects are classified wrongly in
Yes,
that,
yeah.
and you need to find a way to identify that and put them in the right bin.
Yeah, this is because we use just the classes that they were providing. So we want to do the same again with the.
Exactly what you, sorry, I'm Angel Ruiz. It's exactly what you are saying. I mean, it's just depending on the flag that you use and here we were using something that obviously it cannot be. I mean, they are flagged as extended, possibly extended, but maybe it's due to some defect, something wrong in the image, but not physically. Yeah, so we have to go back to the secure point because I think it makes more sense than trying to put things in the extended using those flags. Yeah.
All right. Any other question?
Hi, Ektoras, Matt Page here. I didn't understand why you were advocating that your type 1 sources were red quasars with more dust. What was the criterion that was driving you to that?
You mean
Conclusion.
the?
You said you're near the end, you said the type 1 objects in the X-ray sample. Yeah.
So here, actually, it's the type 1 that they're applying the same magnitude distribution in the optical. So the question was actually why they are not selected in both methods.
Right.
So through this defeating, we found that the X-ray type 1 sources have a higher polar dust in the direction of sight. So this is indication for red QSOs. So
But this is on the basis of optical color or something like that.
no, this is based on the SED fitting.
But the SED fitting in the end
Yeah.
is on rest frame optical color or UV color or something. It's the shape of the SED in the rest frame UV and optical. Okay, thank you.
All right, we'll have to move to the next presentation. Let's thanks Ektoras again.